Hello and welcome to section 4.6. This is on Newton's method. And let's get straight into the main ideas here of Newton's method. And the big thing that we're going to do with this, Newton's method allows us to numerically approximate roots of a function, since you can't always solve for roots in a nice, clean way. This is true. So Newton's method is going to allow us to get an approximate value. So this is not finding an exact value. If there are radicals, pi, e, things like that, those will be in their approximate forms. This is not a nice, clean answer, okay? So these are for roots of a function. And if you'll recall from algebra, a root is where a function crosses the x-axis, like that would be a root right there. So the big idea is that we are solving the equation f of x equals 0. Okay, so if we solve that for x, that x value would be a root. Okay, anywhere where the function equals 0. Okay, so we are going to approximate these roots because, you know, back in algebra, if you had a function and you were looking for the roots, you would just set f of x equal to 0. We've done that a lot in this class, actually, finding critical points, finding intercepts, all sorts of things like that. And frequently the functions are set up nice enough so that you can solve that equation for x in a nice closed form and find the actual value of the root. Now, when you get up to using more complicated functions, and believe me, there are some really complicated ones out there, you can't always do that, all right? You can set it up, you can say f of x equals 0, but you won't always have a method to use to actually solve that equation for x. So the best we can do is to make a numerical approximation with the help of technology, computer programs, calculators, etc., to help us get as good of an approximation as we can to those roots. So you might not have a nice, clean, closed form, but you can at least find where that root is going to be. Okay. Now, the general idea of how this method works is that it uses tangent lines, and that's why we talk about this method in calc. So we're going to use tangent lines to gradually get closer and closer to a root. And the idea here is similar, you're going to notice, to the idea of linearization, which we talked about last chapter. So linearization, recall, was the process where we used a tangent line to approximate the behavior of a function. So you can maybe kind of guess how this is going to be similar. We are going to use a tangent line to approximate the behavior of a function, and that will lead us to approximating the roots of that function. All right, so let's see how this works. Graphically here, let's put in a generic function f of x. Okay, so here's x and f of x. All right. Make sure when you're sketching your function, yours might look different from mine. That's fine. Just make sure it has a root somewhere because we are gonna be looking for that. Okay, so I'm gonna make a nice sketch like this. Nothing too fancy. That's our function f of x. And so with Newton's method, again, yes, we are going to be trying to approximate the root, which is right here on this graph. Okay, we want this right here. We want that x value. Okay, But let's say that whatever this function is, it doesn't look too complicated, but let's say it's secretly really complicated behind the scenes. And we can't just solve f of x equals 0 in a nice, clean way. So to use Newton's method, we are going to make a guess as to where that root is. And we might not be that close. Okay, let's say we guess, okay, the root is somewhere around this x value. Okay, we're going to call that x1 to give ourselves a little starting point. Start here. Okay. So this, you'll see this called by a couple different names, either x sub 1 or x sub 0. At the moment, I can't remember which one the book tends to use most, but either one of those, we're just going to be kind of incrementing up that little subscript on x. So whether you start at 1 or 0, just be consistent. Okay, so that's our starting guess. And as you can see, it's really not too close to the root on this picture. But we are going to use our starting point guess to create a tangent line to the function. Okay, so this is the point x1 comma f of x1. And based on that, we will make a tangent line. Let's see if I can draw something nice and linear here. Okay. It's not great, but it'll work. Okay, so that, oops, there it went. Okay, there we go. That's a tangent line. So there's our tangent line to the function at x1 comma f of x1. And we can use that tangent line to approximate the behavior of the function. So even if we can't find the function's root directly, with lines, if you have the equation of a line, you can solve that quickly to find the root for that line. The root for the line is going to be right here. Okay, we're going to call this value x2. And I'll just note here that this is the root given by the first tangent line. Okay, and yes, that says the first tangent line. So we are going to create another tangent line based off of this new guess, this new value of x. Okay, you can see that it did move us closer to finding the actual root that we want, but we're not quite there yet. So let's take this up. There's a point right there. That's x2 comma f of x2. And we'll create a tangent line based on that point now. Okay, let's see. Tangent lines are kind of hard to draw, don't you think? I think they're kind of hard to draw sometimes, but I do have to draw a lot of them. That looked more like a tangent curve. Okay, let's make this linear. As linear as possible. Okay. Well, the top's a little wonky, but we'll call that a tangent line, sure. I think I also, there's our previous tangent line. Okay. So the green line, yes, pretend it's a really straight linear line. This green line is our new tangent line to the function that we're going to consider. And so we are going to look at the root of that tangent line now, because again, lines, easy to find the root. And let's zoom in a little bit. You can see the root for that second tangent line is right here. We're going to call that one x sub 3. Okay. This is the root given by the second tangent line. Okay. And then if you wanted to keep going from here, you could. Notice that we've, again, gotten much closer to our root that we're actually trying to find. Okay, we want this. Right now we're here at x3, so the distance between those two values has shrunk to just that much now, which is not too bad. Depending on how accurate you need to be for your problem, let's say that you're, researching something, depending how accurate you need that value to be, x3 here, that might be a fine approximation for the root. You might decide that, okay, this is an acceptable amount of difference, acceptable amount of error there, and we're fine. Or you could create another tangent line based on x3. Look at how you wouldn't have to go far at all. Okay. And then to create that tangent line, something along these lines. And you'll see that that tangent line actually looks like it passes right through the value that we want. Now that might not be exact. Notice how my drawing is a little bit thick here. The point covers a fair amount of area there. But that approximation, this root right here, might be close enough, or you might keep going if you could zoom in even further. But that's the idea, is that we're using these tangent lines to edge ourselves closer and closer to the actual root of the function. Okay, so these are creating approximations to the root, but the approximation gets more and more accurate. We started with this guess, and then we got closer, and then we got closer, and we could get even closer than that if we needed to. So there's the idea of Newton's method. And in the next video, we'll find out the formula for doing this.